I think stage is yours. Coupling of material properties. I think it is a bit interactive as far as I know. Some intermediate, yeah. So one last lecture for today before we go to the city center later on. But Emmanuel,
thank you.
We concentrate on your stuff. Thank you.
Okay. First of all, I would like to thank Véronique for his patience and for all what she did for the organization of this summer school, because, you know, I'm French, now you know, so I'm generally late, so I didn't answer her as soon as possible as expected, and she was very patient, and then everything likes to be well, so thank you again, Véronique. So, as two previous presentators, 15 years ago, I was a mechanist. And I also worked on composites with carbon fibers and resin. And I met Jacques, you learned just before, and I shifted to the dark force. And now I'm trying to do chemistry. And I hope you will enjoy. So the title is Coupling of Material Properties. You will see that some figures are similar to those of Jacques, because we shared a part of his work. I learned from him at the beginning. So I will skip quite fast, because I planned on practical. So we will do these practicals, and I think it's also a good thing for you, because I can imagine what you have in your brain, and probably if we calculate the Gibbs energy of your brain, we will conclude that it is a liquid phase probably. So we will try to lighter this day. Okay. So as introduction, just focusing on some insights, very important insight from my opinion, regarding the corrosion of refractory by slag as a reactive inclination process. Okay, so you recognize this figure shown already by Jacques, and you can see that effectively at the beginning there is a surface mechanism of reaction, followed by a volume mechanism, and of course with local equilibrium as mentioned. Also, you have to keep in mind the gradient in temperature inside the refractory, but there is something very strange in this state, because why the reaction zone is different from the infiltration zone, okay? Okay, we can say it is due to the temperature gradient, due to the viscosity increase, etc., etc. But nevertheless, imagine we are still at more than 1000 degrees, and there is no reaction in this part. Why? So I will try to show you that it is a problem of kinetics also. So focus on the surface mechanism, and starting with the wettability, because the slag needs to wet the sample, the sample at my lab scale, and the refractory block at industrial scale, to react with it. So I skip this part very quickly, because you already have been learned about this point. So the dissolution process. This dissolution process, you recognize the figure with a saturation limit, etc., etc. You have to keep in mind that this process occurs at the interface between the slag and the hot face of the refractory, but also inside the refractory. Then you have not to imagine that this part is the block, but grains, because the slag will infiltrate the product network and then react with the grains. Okay, so of course the geometry is not as simple. And of course, depending on the composition of a slag, of the composition of the grains or of a refractory, we can observe a direct dissolution without no limit, and or an indirect dissolution with a precipitation of a kind of protective layer limiting the reaction. And this has been, from the kinetic point of view, described by Nernst equation relating the concentration rate with the gradient in concentration and the diffusion coefficient and the thickness of the layer. Here it is a very simple problem and a very simple model. Because if we consider the reality, D depends on the composition and on the also temperature. Because D is the coefficient diffusion in the slag, okay, which is like a pump, and this slag pumps all the refractories. It eats all the refractory, providing there is slag enough. But in this layer, the composition changes a lot. That means that the diffusion coefficient changes also. Why? Because it is a liquid phase, a unique liquid phase. That means that there are some atoms, for instance, of aluminum, of calcium, and of oxygen, to keep the example, to take the example of CaO Al2O3 slag. What is inside? It is a liquid, but the atoms cannot do what they want. They have strong relation between themselves due to the local organization with calcium, aluminum, and oxygen. The aluminum have 4 or 5 oxygen around them, creating a tetrahedron, okay? And sometimes they share an oxygen, a bonding oxygen, with another tetrahedron, etc., and you have a polymeric chain, okay? And depending on the length of the chain, the mobility of the atoms, the oxygen, the aluminum, and also the calcium will change. Where are the calcium? If the calcium is not too much in quantity, then the calcium will behave as a network former. That means that they will be close to an bonding oxygen to compensate the charge, and they will be happy like that. Of course, it is dynamic, so they change every time in a very, very short time. Picosecond, we are talking about picosecond, okay? But nevertheless, you can imagine this image, okay? If you add more and more calcium, what is happening? There will be no place any longer for the calcium because all bonding oxygen have been are already occupied by the previous calcium atom. So imagine you are a new calcium atom and you have to take your place. What will you do? You will break the chain because you need an oxygen to compensate the charge. And then the calcium will become a modifier of the network. So that means that the mobility inside the liquid changes with the composition, and then the diffusion changes also. So this problem is a very simple equation, but in reality, it is much more complex, of course. This is one point I wanted to highlight. The second point is that in the previous slide, we imagine that the slag is static, okay, nothing changed. But sometimes the slag is removed, okay, and renewed regularly because we are in a process with a circulating flow, okay? And also because even in case of static situation, there is Marangoni effect in the triple point corresponding to the interface between the slag, the metal, and the slag, the air, sorry for the top part, and the refractory, or below the slag, the metal, and the refractory. And in both cases, the surface tension, which is dependent on the composition, will create a movement, a circulation of the slag, and then it is like if you renew always the composition of the slag. That means that in this case, you cannot reach the saturation because you are changing the composition of the slag each time. So this slag is always hungry. He wants to eat refractories in this case, okay? So this is a point we can observe in reality, of course. Another point is now the focus on infiltration due to the capillary force. So you recognize Dresden and also Jacques presented the Lucas-Washburn law, okay? And he also, Jacques presented this equation corresponding to the saturation. Okay, we can see here the engine, the force, the driving force, okay? The capillary pressure versus the saturation, okay? Saturation is between 0 and 1. 0 when there is no slag, 1 when the pores is completely full of slag. This is a complicated function with a big nonlinearity. So it is difficult to simulate this, to solve this equation due to the big, strong nonlinearity of this function. And it is time consuming for the simulation. But, okay, this is an important parameter, but from my opinion, it is not the most. Why? Because this part, behind this function, there is the wettability, the capillary pressure, etc. A lot of things we are not able to simulate at a macro scale, okay? So whatever this function, you can consider that, okay, this block of refractory has a capillary pressure resulting from its porous network. Okay. Most important is the permeability here, the intrinsic permeability and the viscosity. And if you have a choice to determine one of these parameters, please choose the viscosity, because viscosity is, from my opinion, the most important point, the most important parameter, okay? We worked a lot on the measurement of permeability, but nevertheless, the viscosity is the most important. And consider that permeability and viscosity are the brakes. This is the engine, this is the brake, okay, which limit. Okay, normally here we should see a movie corresponding to a reactive inclination process, but unfortunately the codec of this movie is not implemented in this computer, so the computer is not able to read my file. But you can imagine this is a block of refractory with few pellets, okay, put on the top, and then we could look at the temperature, and then we could observe that, of course, with the increase in temperature, the pellets start to deform, to wet, and to impregnate, okay? This is what we could expect, and it corresponds to this schema. Okay, if we do that on a simple sample made of alumina with big porosity to emphasize the process, and we observe, we cut the sample after the test, and we look at with SEM, and this is what we can observe. The alumina grains and the porous network here, a channel of the pores, which has been filled by the slag, and due to the indirect dissolution, you can observe different monolayers, as Torsten showed also this morning, with the hexaluminate, the dealuminate, and the monoaluminate of calcium, and the rest of slag here. What I want to explain with this figure is, first, due to this indirect dissolution, this process clogs the porous network. Then it limits the inclination, okay? But there is a second problem. These phases, and especially the hexaluminate of calcium, is expansive. The volume occupied by this phase is more than the sum of the volumes occupied by the reactants, okay? Then, that means that, imagine you are the CA6, and you are here, and you are to grow. But there is a lot of things around you, and you cannot grow. Then what you will create? You will create stress. And this stress may have an effect on the mechanics. That's why chemistry and mechanics are strongly coupled in a process of corrosion. Okay. Oh, I'm happy because when I tried, this movie didn't work. Now it works. Okay. This is me, Manu. Okay. As you can see, in holidays, I like to eat. I like good things, okay? So I need to make sport. Okay, so now we will skip to the, if I succeed, okay, I have to switch to the other presentation. I'm lost. Let me check. 7.1. Okay.
Got it? Yeah.
Yes, it's okay. So normally I have to, okay, here, escape. No, not escape. Stop. Okay. Okay. Nice. Now here. Okay. So let's play doctors. It is about the incineration, the example Jacques presented just before for the waste to energy incineration. So some insights. Okay. And here you have a schematic representation of this facility with a burnt waste here, the chimney, and inside this chimney on the walls, beside the wall, there are water wall tubes containing water steam so that you can keep the heat from the fume. Okay. Of course, what we create as waste are very reactive. So the fume is very reactive. So that's why we have to protect this tube. And that's why we apply some refractory tiles, generally made of silicon carbide, because silicon carbide has good thermal properties to transfer the heat and at the same time a good resistance, chemical resistance. Okay. And we will focus on this part here with a contact between the walls and the ashes. Okay. So this is the tiles. Okay. I skip because Jack already presented it. So, but to have an overall idea of what about it is, on the top, no reaction. You can keep these tiles 5 years, 10 years if you want. Okay. In the middle, this is the example Jacques showed you. So there are some difficulties with the wear of the tiles, and you have to change maybe every 2-3 years. Okay. And in this part, you have to change some of the tiles every year. So you have to stop the facility, wait for the cooling, etc., etc. So it's very expensive. So you have no time to do that. Okay. So if you are able to multiply the lifetime of these tiles, it will be nice. Okay. This was the challenge. Okay. So when we have such study, the first step is to elaborate the diagnostic. If you go to the doctor, what you want from him, what you expect is first, he's able to exactly say what you have. Okay. This is what you will have to do now. Your mission, not mine, your mission is to find the tiles wear mechanism located in the bottom of this facility. So to do that, take your phone, please, and flash this QR code. Or if you cannot, you can also Google WOOCLAP, WOOCLAP, like it is written here, and enter directly the code TJSUJO. Okay, and you will join the event. So don't be afraid because maybe nothing is happening right now because I have to start the application. Okay. But please follow me and do the things step by step. I have now something to do. Okay. Normally it is somewhere here. No, it isn't a problem. Oh, now I think I can do it. Okay. 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 Okay, now it's connected. So normally you should be able to do something. What you will have to do is first, it's not easy to play with a computer. It is an experiment, to be honest. I already use this kind of application, but never with so many people. So I don't know if it will work or not. You are my samples. Okay, so you have to choose a team with a leader. As you can see, with different skills, okay? Doctors or inspectors or detectives, you choose what you want, who you want, okay? It is due to the fact that we will have some survey and some results, okay? So now, normally, it's not so easy. No, sorry. You can also do that online, of course. But on my computer, it was easier, to be honest. I prepared for a long time this exercise, but it is not so easy now because, okay, here. Ah, okay, thank you, it works. I don't see it now, but here, yes, okay. I don't know why, but nevertheless, it works. Okay. A lot of windows. Okay, it is here. Maybe if I put it here. It is an experiment. Let me check. There is something wrong. Okay, what I can do. But it works, as you can see. Okay, but normally I should shift to the next step, but I cannot because I have not this window. Where is my cursor? Here? No. I did a mistake because what I can do is stop. Ah, now I see it. Okay, but I'm close to the screen and I didn't see it. Okay, so where is the cursor now? Here. Okay. Okay. I need. Okay. Yes, it will come. Don't worry about that. But no one will leave the room until we solve the problem. Okay. Okay. So next step. Next step. Let's look at. The problem is I have to switch between the two screens. Okay. Let's look at the general properties and the composition of this tile. Okay. And the question is, yes, okay, you understand. Nice. You are faster than me. Thank you very much for your help. Okay. Yes, agree. It is rather complex. And Jacques showed you that it was important to try to simulate the pressing of the tile because you want to control the porosity. Okay, because the porosity is the porous network, it is the permeability, it is the possibility for the slag or the ash or the gases to infiltrate. So that's why it is important. So you can see, okay, the shape is complicated. So that means that okay, it's laborious. Okay. Yes, it is a complex geometry. That's why it is pressed and sintered with high silicon carbide content because of properties I mentioned. And silicon carbide is difficult to sinter. That means that we have to adapt the matrix so that it is possible to elaborate such geometry. Okay, and that's why we will see that we have a clay as the bonding phase, and this bonding phase plays a very important role. Okay, this is the bonding phase. Okay, and you can see, oh, the table is not very clear, but nevertheless, you can see that the big content of silica, okay, it is a clay. Actually, it is bentonite phase, okay, with a lot of silica, alumina, then calcia, and some other fluxes. Okay. Each time you will see the logo WUCLAP on the top on the left, that means that there will be a question. So if I skip a question, please remind me. So bonding phase is bentonite with high silica content and fluxing oxide. You have to now to understand that I'm giving you some insights and you have to create the puzzle, okay, to solve the puzzle with different information from all our observation. This is exactly what we do when we have to elaborate a diagnostic of corrosion to understand. Keep in mind that for our situation, in our situation, it takes at least 1 year, maybe sometimes 1 year and a half, and maybe even two years, depending. Because again, it is important that the doctor gives you the true diagnostic. If he makes an error, you're dead. Okay? So, 6 tiles porosity, WUCLAP. Normally now I understand how to do like that. Where is it? No, I don't know why. It's okay. So next question. How do you describe the pore size? Small, medium, big. Exactly. Consulting. But it is your opinion and you will elaborate the diagnostic from your opinion. So that's why it is important. Of course, you can change your opinion with the time, for sure, because you are understanding along with the time. Okay. Answer. Fairly high open porosity due to the pressing conditions. I mentioned the complex geometry and the pressing, uniaxial pressing. Okay, so yes, the open porosity is fairly high, nevertheless, because you can see the value and also 19% in the volume, okay? Somewhere 15%, so 15% is reasonable, 19 starts to be high, but if you look at where it is in an area where the ash doesn't contact, so it is not so dangerous for the tile. But what you can see also is the pore size distribution, and you can see that where it is difficult to press, you will get the bigger pores, of course, because you will have difficulty to compress the grains and to densify the material. Fairly big pores, high heterogeneity in the volume due to the power creep also. Okay. Next. Slag deposit characterization. We have a sound tile. Now, what about the deposit? Slag deposit composition. What do you observe? Look at, we took three the deposits, sorry, in 3 plants, and we analyzed them to look at their composition. Okay, why it is important to do such a work? WUCLAP. I have to do it twice, I think, to... No. No. Yes. Okay. How can you describe the deposits? About the microstructure, about the composition, and also about the... Okay, but you can see, okay, you can move, okay? Okay, it is free due to the time. Yes, why not? But we are not sure because we have not yet the complete composition. Okay, but we can see effectively some parts. Okay, but don't forget that this deposit comes from the burnt waste. Okay, multi-layer. Yes, right. You can see multi-layers. That means that the deposit created different layers with a time. Okay. Highly porous, absolutely. Good observation also. It is very porous. Okay. Yes. Basicity or acidity around 1. Okay. Not so much acid or basic. Rich in sodium also. Okay. So if we continue. Before that, what is important? Yes. Before that, sport again. Deposit under the form of multi-layers, low variability from one plant to another one. This is a very important point. Why? Because if you want to understand and if you perform some calculations, you need to know the composition. But if the composition varies a lot between different plants, the solution you will give will depend on the plant you are applying your solution. So that's why it is very important to take different samples from different plants and to have an idea about this variability. Then, a second advantage from this no variability is the fact that you are able to reproduce this slag at the lab scale and to perform some lab test. Okay, if the slag was very different from one plant to another one, which composition do you choose for your lab test? You don't know. So we were very happy and very lucky to observe that the different deposits has almost the same composition. Okay. The properties of this deposit or slag, okay, you can see, of course, with the same composition, we can expect some similar properties. The solidus, the liquidus, the primary phase of crystallization during the cooling, okay, the basicity, as I mentioned, and the viscosity of liquid phase. So the viscosity is between 11 and 4 or 5 Pascal second, okay. So if you want to have an idea about this value of this viscosity, it is between honey and molasses. Okay, so it is viscous, but not so much. This is also a very important point. And due to the liquidus temperature, that means that the deposit is partially melted in contact with the wall at this temperature. Because at the beginning, I skip very quickly, but at the beginning, I saw the temperature, the operative temperature, which was 1,200. So a little bit lower than the liquidus temperature. That means that a part of this deposit is liquid with a viscosity calculated from the composition. Okay. Now looking at the interaction between the tile and the deposit, post-mortem analysis, that means. Okay, so this is the result. Okay, this is a very important point because the diagnostic, you need the sound tile, you need to know the slag, and you need to know the interaction between both. Okay, so who clap? Okay, I learn. How is the deposit in contact with the tile hot phase? Solid, partially liquid, or liquid? I gave the answer. I skipped this part, sorry. It is partially liquid, okay, or partially solid, of course. Okay. Next question. If you look at the tile here on the top left, okay, what do you think about this figure? Not this figure, this photo, okay? Does it make you think about something in particular? What can you see, observe? What can you see, what can you observe? Capillarity, not so much. Spongy, right, spongy. like pumice. Okay, you can observe some craters. Okay, and these craters has a size much bigger than the size of the biggest grain of silicon carbide. That means that it is not a silicon carbide which has been detached. It is something different. Okay, so okay, second examination. I don't know. Okay, crater-like cavities on the hot face, no cracks, no swelling in the corroded tile. This is what we observed in the medium 8. Okay, due to the infiltration of the gases, etc., etc. I skip the mechanism in this part, but in this part, it is completely different. That means, of course, that the solution you have to find for these new tiles on the bottom, either you have to choose and to mix two different tiles, or you have also to keep in mind what is happening 9 meters above, because the tile has to resist to the corrosion induced by the gas infiltration and the corrosion induced by the contact with deposit. Okay, so it becomes more complicated, of course. Big pores at the interface, I mentioned it. Okay, you can see here. And if you think about how pumice is created in geology, there is a gas. Okay, so here we can keep in mind somewhere, we don't know where exactly, but we can imagine that gas is involved in this process. Okay, post-mortem analysis indicated us that we observed around the finest silicon carbide grains, silica, so corresponding to the oxidation. First, we also observed silicon carbide grains isolated without any matrix. The matrix disappeared. Okay, this explains the decohesive process of a part of a tile and then leaving the tile, and that's why we observe these craters. And presence of alkali in the bonding phase, which was not at the beginning, okay, and coming from the deposit. We perform some calculation from this composition, okay, in this zone, and then we observe that we add liquid phase and solid phases here. Okay, with a comment here, it is not so important. What we also did, we calculated the viscosity of this liquid, and now we observe a very high viscosity compared to the viscosity of the deposit alone. Okay? And if you want to have an idea what about, the honey and the molasses were somewhere above this figure, and now we are in this area corresponding to silicon sealant, for instance. So something very, very viscous. Next question, because there is screw cap. Okay. What is the difference between slag alone and slag plus deposit? You have to vote. I look at the time, so I go fast. Okay. First, hot phase temperature, 1,200. Okay, liquid temperature, 1,000 this time. So lower than the interface temperature. At the beginning, the slag, the deposit is partially liquid, and now it is solid. Okay, it is completely liquid. It is solid, sorry. It is liquid. Oh, okay. It is completely liquid. Okay, because the temperature is much more lower. Bonding phase is completely dissolved when in contact with the deposit. Okay, even the slag is only partially liquid, it's enough to dissolve the interface and the bonding phases. So that's why we observed the decomposition of the microstructure with isolated grains of silicon carbide. So again, we perform some calculation in concentrated zone around the oxidized silicon carbide with silica, okay, just around due to the composition. And what we observed was effectively that the viscosity increases strongly, okay, here as you can see, okay, depending on the composition of the liquid, and you have all the calculation we made here with some magnification here around this part and around this part for this, okay? But what you have to keep in mind is the liquidus temperature and the evolution of the viscosity, which is something which becomes very, very viscous. And this is also an important point. So hot phase, okay, I already mentioned it. Okay. If you look at deeper, at the interface, we can observe some different reactions with the formation of wollastonite. I skip this part. It is not the most important, not right now at least. Okay. We also perform XRD analysis, and we perform now laboratory tests. Okay. Because we have in mind something. Okay. We have an idea about what is happening. And now we would like to reproduce it at the scale of the laboratory to check if you are aware, if we are right or not. We perform some calculation for thermodynamic calculation, and then we would like to try if it is correct. First, to confirm our assumption. And the second reason is that if we are able to reproduce the mechanism, the corrosion mechanism at the laboratory scale, then we are able to play with the formulation of the refractory bricks to try, or if we had something else, etc., etc. And we perform tests, we perform calculation, and it is okay. We can compare the results. If we are not able to reproduce the corrosion process at a lab scale, what is happening at industrial scale, then we cannot play with the composition. We cannot say to the CEO of a plant, okay, guy, we will change your tile. We are not sure about the problem, but we will try and we will see. Maybe we'll have to stop your plant in one day. No, it's not possible. Of course, we have to be sure and we have to be convincing to propose something else. Okay, this is what we did. I don't look at the time where I am. 40 minutes? Okay. So I will continue without recap because with this, it is too time consuming. I'm very sorry for that. But I hope you will be more active for the end of this day. What we did is very simply, we put only slag in a crucible, okay? And we put slag plus the bonding phase. And we observe a difference. You can see that the slag maybe react a little bit with the crucible, but it is not the problem. You can see that it wets the crucible, but okay, it is just like a glass in the end. Okay, it is not surprising considering the content of silica. In reaction with the bonding phase, we observe bubbles. Okay. Remember what we observed on the tile with the craters corresponding to the pumice formation, etc., etc. We analyzed and we saw different oxides, and we conclude the most important conclusion, the deposit wets the crucible, deposit plus silicon carbide grains, strong interaction between deposit and silicon carbide, and a lot of trapped bubbles. Okay, normally, if a liquid is not viscous, the bubbles have time to leave. Here, not. Okay, we didn't quench the sample. We're just cooling down free. Okay. So this is the formation of the wollastonite. I skip it. Maybe I will have time to explain you. And now it's time for the corrosion mechanism. But I said I will stop sorry. But it is how it happened. I stopped the WCAP, but nevertheless, I will go back just a minute after that. This is the mechanisms. Okay, at the beginning, you have the thick in the refractory, the SIC, sorry, SIC is French, the SIC refractory tile, okay, with a deposit in contact, the dissolution of the matrix, okay, and the oxidation of a silicon carbide producing CO2 with a high viscosity of a liquid phase, trapping the bubbles, creating a void, not exactly a void, but a phase with only gases, a volume with only gases, and the pressure increasing. The wollastonite, nevertheless, plays also a role because the wollastonite is in this area where the calcium oxide diffuses in the deposit to join the tile and reacting with the silica produced by the oxidation, producing wollastonite. Wollastonite is also an expansive phase. That means it creates stress, promoting cracks, and these cracks promoting the separation of a deposit, but of a deposit with a part of the tiles, producing the craters we observed. Okay? So now, if you have well understood the process, come on, okay? Ah. Be patient, panic. Okay. Don't panic. Okay. No, sorry. I was too quickly. Yes. You have 4 figures, A, B, C, D. And now I ask you to build, to sort, to order the different steps of this mechanism corresponding to the rear of the tiles. Okay? So the answer is, you can try if you want, but the answer is, of course, this part. At the beginning, we have a sound tile, a new tile in contact with deposit. The reaction we saw just before, creating the separation of the deposit, bringing with it a part of a tile, creating craters, and at the same time, a part of the other oxides, remember the sodium oxide, for instance, migrating inside in the depth of the tile. That means that the next time a new deposit will be applied here, it will react not only with a sound tile, but also with a sound tile containing all the oxide which have migrated before, okay, and accelerating the damage. Actually, what I wanted to say, the doctors and the inspectors I proposed you at the beginning are not the good doctor. The good doctor is Audrey Tixier. Maybe some of you know her, because she was awarded by the Irish Award, and also she had the best PhD French of the French ceramic group in 2023. And if you want to get more details about this mechanisms, because I skip a lot of things, you can have details on this paper, of course. And she did a very nice work. After the diagnostic, after the new formulation, I cannot give you formulation because it's confidential, of course, okay? But she also performed the mechanical calculation for the pressing of the tiles in 3 years, okay? And this project was called twice because the objective was to multiply by 2 the lifetime of the refractory. And we installed new tiles in the plants, and we tested. We extracted tiles after 6 months, after 1 year, after 1 year, and 6 months after 2 years. And finally, the score was 1.8. So not so bad regarding the target, which was 2. So thank you, Audrey, for this work. And I think I will stop now. Thank you very much. I hope you enjoyed.